So let's begin. It's a great pleasure to have our good friend, Andrew Schopieray, back here at our quantum symmetry seminar. So he will talk about his very recent work on fixed point free fusion automorphisms. Please, Andrew.
All right, thank you, Elong, and thank you to Sebastian for inviting me. Pretty much maybe an hour after I posted my paper, I got an invite from Sebastian to talk about it, that's really good because I'll probably remember more about my paper now than ever in the future. So yeah, it's not good to give talks, 3 or 4 years after you've written something. So this paper actually started from a meeting, a very small focused research group that we had in Banff last December, and it just arose from a question, which was, do we have any fixed point free autoequivalences of these fusion categories that are interesting? And it's not something that had really been touched on before. So this is a very, very first effort to start looking into, what types of these things exist, if they do. And it actually ties into a lot of other things that I was already thinking about. So it's a very good topic that I think should be thought about a lot more. So an outline of what I'm going to talk about is I'll first start with a little bit of history, because the idea of studying these fixed point free automorphisms really was motivated from the study of finite groups. So I'll talk a little bit about the history, not too much, just a few slides. And then I'll talk about sort of the definitions of everything that we're going to need to discuss the rest of the talk. So that'll be fusion rings, a generalization of finite groups, their representation theory and automorphisms, etc. And we should have plenty of time to get to what I really wanted to think about, which was how we can study these in terms of fusion categories. So that's another level of structure that's very interesting, but quite difficult to study in general. And this will tie into a couple of other topics that I've already thought about a bit. So one of these, of course, is the fixed point free autoequivalences. Another is fusion categories which have odd dimension, which have been studied by others before. And also something which has been very recently studied by Jingcheng Dong and his co-authors, which are fusion categories which have a very large, in fact, maximal proper subcategory. So all these things will tie together quite nicely as we go along. But this is primarily based on, again, the paper that I posted last week. It appeared on Monday, but here's the archive identifier if you want to look it up. So moving on to our history, which is fixed point free automorphisms of finite groups, we want to start with the very smallest possible order of these automorphisms, which is, of course, 2. So we'll look at fixed point free involutions of finite groups. So we'll let G be a group and F be an automorphism. And we're going to say that it's fixed point free if the only fixed point is the identity. So it's not quite fixed point free, but it's as close to fixed point free as you could possibly get. And this phrase has been used for over 100 years in the group theory literature, so I don't dare try to change it at this point. So fixed point free means one fixed point. But fixed point free automorphisms are incredibly rare. So amongst finite groups, the ones that have them are just a very, very small, measure 0 subset of all of the finite groups. And if you specify the specific primes, you can be incredibly specific, especially with the order p equals 2. So this is actually an exercise in an undergraduate abstract algebra textbook that is popular in North America called Dummett and Foote. So if I have a finite group with a fixed point free involution, so something that's order 2, then you can prove that the map, which takes the group element and multiplies the image of F with its inverse, that in fact, this is an automorphism of your group. And in particular, it's surjective. And this means if I evaluated F, I just use the formula, I get out the inverse. And so this must be true for every element of my group. So this is just a very quick proof that the only fixed point free involution of a finite group is in fact inversion. So we know exactly what this map is. And if inversion is a group homomorphism, then you can easily show that your group must be abelian. So fixed point free automorphisms of order 2 exist for exactly one type of group. They are the abelian groups of odd order. And there is no choice for what your fixed point free involution is. It must be the inverse map. So this actually is I've never seen it attributed to an individual. It's an exercise in textbooks that are over 100 years old. So this is just a very basic fact. But when you move up in prime orders, say we go to the prime p equals 3, things get slightly more difficult. We have to go to an exercise in a graduate text in mathematics. So Robinson's book on group theory. So an exercise in the section about fixed point free automorphisms is for the student to show that if you have a fixed point free automorphism of order 3, then your group must be nilpotent with nilpotency class at most 2. So nilpotent groups are quite rare, and nilpotent groups that have nilpotency class 1 and 2 are very rare indeed. So examples of this, you have your abelian groups, your nilpotency class 1, like the Klein 4 group. So the Klein 4 group has those 3 non-trivial elements, and you can shuffle them around in any way you want. So in particular, there's a fixed point free automorphism of order 3. If you want a non-abelian example, or something that has nilpotency class 2, then you have to go all the way up to order 64. So if you look in the GAP small groups library, the smallest 2 are 64 elements, and they're index number 242 and 245. So they're too complicated to care what their structure is, but they're non-abelian groups with fixed point free automorphisms of order 3. And 64 for the objects that we're going to be talking about is a very large number. For groups, it's not quite that large, but for when we get into fusion rings and fusion categories, this already is quite a large jump from the easier examples. So you may have heard of a group theorist named John Thompson. He won a Fields Medal, and you can look up his PhD thesis at the University of Chicago, and you'll see that it's 10 pages long. And in his doctoral thesis, he proved that if you have a finite group with a fixed point free automorphism of prime order, then your group must be nilpotent. So nilpotency is something that comes along with having these fixed point free automorphisms of prime order, or if you look at more general orders, as long as you have a fixed point free automorphism coprime to the order of the group, you get nilpotency. And that's something that's verifiable by a computer nowadays because we have the classification of finite simple groups. But at the time, this was an incredibly deep result, and it was deep enough that actually there's a New York Times article from 1959 about the fact that he proved this. So it was seen as a very large jump forward at the time. But that's enough about the history. What we really want to is jump into the modern times, where we're not just looking at groups, we're looking at fusion rings, which are a grand generalization of finite groups. And in particular, they're generalizations of the integral group rings. So we can freely add all of our group elements, but we can also multiply them together in the usual way. So as a definition, a fusion ring is going to be an associative and unital ring, which is free as a Z module. So this means I can add any number of these elements that I want, any multiple of them. And I want to have a distinguished basis for this freeness. So I'm going to pick a basis that must include my unit, and it contains some other elements of my ring. So this is subject to quite a few conditions. So first of all, we call the rank of our fusion ring the number of basis elements. So if I say rank, you'll know that that's what I'm referring to. Now, when I multiply these ring elements together, I'm not going to get basis elements in general. Otherwise, I would just end up with just a normal group. I'm going to get some big sum of these basis elements. And we want to stipulate that those are going to appear with non-negative integer coefficients. So this is sort of a positivity constraint that we're imposing. And we call these the fusion rules of our fusion ring. And lastly, we want a notion of inversion. But because when I multiply two things together, I'm not just getting one element, then my inversion isn't going to look like the inverse in a finite group. It's going to be slightly weaker. So the condition for our inversion, or what we call duality, is that when I multiply something with its dual, I get a copy of the tensor unit or of the multiplicative unit with multiplicity 1. So that's my only stipulation. I could have a whole bunch of other elements appearing in that product in general. So the definition is what it is, but you're very familiar with many examples. And the examples are very easy to write down because they're completely determined by our rank matrices, and I only need our rank number of them. So we only need n cubed non-negative integers to completely describe these fusion rings. So starting with very small ones, if you only have one basis element, because of our duality constraint and our positivity, you must have that it multiplies by itself to be 1. So there's only one fusion ring of rank 1. But already in rank 2, we have an infinite number of them, which are indexed by the non-negative integers. So the unit, of course, has to do what the unit does. But our other element, when I multiply it by itself, I'm going to get one copy of the unit, but I can have any number of copies, non-negative number of copies of that object that I want. So there's an infinite number of fusion rings of rank 2. And if you go to rank 3, it's actually possible to write them all down, but you wouldn't want to go much further than this. So these are parameterized by 4 non-negative integers. And the fusion matrices look a little bit like this. So the constraint that we're insisting upon here is the associativity of the multiplication. So if I pick any 4 non-negative integers that satisfy this constraint, then these 3 fusion matrices describe a fusion ring. So there's sort of 4 times the number of fusion rings in rank 2, but you'll notice that I made a small assumption. So you can see that these matrices are symmetric. So this implies that these elements are their own duals. So when I multiply it by itself, that's when I get a 1 appearing in its decomposition. So this is assuming that my rank is self-dual. But there's one other rank 3 fusion ring, which is non-self-dual. So you might recognize these rules as the multiplication in the cyclic group of order 3. So there's 4 times infinity plus 1 fusion rings of rank 3. And you can create lots more examples by looking at finite groups, representations of finite groups, etc. These are very combinatorial objects, so you can have a computer just try to create them randomly and just check that the conditions are satisfied. So it's a very easy to experiment with type of object. So when we talk about automorphisms of fusion rings, we want to be a little bit careful, because a fusion ring is a ring with a specified structure, which is its basis. So I can't just take all automorphisms of my ring. I might not even get something that is a fusion ring back, depending on where the basis is sent. So when we talk about a fusion ring automorphism, what we really want is a permutation of the basis, which extends to a unital ring automorphism of our fusion ring. So this guarantees that the image of the basis is obviously another basis of the same fusion ring, and it preserves a lot of the characteristics that you would want of an automorphism. So for a finite group, automorphisms preserve the order of elements. What that looks like for fusion rings, we have a slightly different notion of order, which is, I'm going to denote these by automorphisms of R, comma B, to specify that we're preserving the basis. And that notion of order that I was talking about for elements is what's called the Frobenius-Perron dimension. So I take my fusion matrices and I use the Frobenius-Perron theorem to imply that I have a maximal real eigenvalue. And that maximal real eigenvalue is called the Frobenius-Perron dimension, but it is also this notion of sort of order that goes along with finite groups. It's the thing that we want preserved by these automorphisms. And if we make this assumption about the basis being preserved, then that's great. This Frobenius-Perron dimension is preserved under automorphisms. So for an example, if we go back to the finite groups themselves, the automorphisms of the fusion ring are just, well, they're exactly the automorphisms of the group. So that's great. This is a strict generalization of the notion. And since our fusion matrices are permutation matrices, their maximal real eigenvalue is 1. So when we see an element that has Frobenius-Perron dimension 1, then that implies that this is sort of part of a group-like structure. It's acting on the basis by permutations. So some people call this invertible or group-like or any number of names, but they're very special, these ones of Frobenius-Perron dimension 1. So an example that'll come back to haunt us in the future is the character ring of the unique non-abelian group of order 21. So this semi-direct product. So if you haven't looked at the representation theory of groups of order PQ in a while, so they're very simple. So I have my trivial representation, and I also have two other representations, which are the non-trivial representations of this C3. So I just have the normal representation theory of C3, and then I have the non-trivial representations of C7 sort of collected together by this C3 action. So I get two other representations that are going to have dimension 3, okay, because they're the non-trivial representations of C7 clumped together by that C3 action. So if you compute the fusion, so if you tensor these representations together or multiply their characters together and decompose them, then you find the following fusion rules. And the Frobenius-Perron dimensions are, well, they're exactly the dimensions of the representations or the degrees of the characters. So this example is going to follow us along because it's really instructive, and it's one of the smallest interesting examples that exist for these fusion rings. So you'll note that there is exactly one non-trivial automorphism of this fusion ring. So all of my elements are not equal to their dual. So duality moves them back and forth. And it's a commutative ring because it's just the character ring, which is always commutative. And so if I take duality as my automorphism, first of all, it is an automorphism because of commutativity. And in fact, it's fixed point free of order 2. So this is our first example of a fixed point free automorphism of a fusion ring that's not just, a fixed point free automorphism of a finite group. So to study our fusion rings, I know this is using the same word for multiple things in a row, but we just looked at an example of a representation theory of a finite group, but we also want to be able to look at the representation theory of fusion rings. So even though I have this fusion ring, which comes from representation theory, I also now want to look at the representation theory of that ring itself, okay? And they're very much related for the finite groups. So in the very standard traditional way, if I have a representation of my ring, then I can take the trace of the images of all the elements of my ring, and I get a character with respect to that representation. So just like we would have characters of finite groups. And just like for finite groups, our irreducible characters, which come from irreducible representations, form an orthogonal basis for the space of all characters. So you can talk about them being orthonormal basis with respect to an inner product, but that's a little bit deeper than I want to go into. But the point is that they act in the same way. And so it makes sense to talk about the character table of my fusion ring. So I can take all of my irreducible representations, look at their characters, and I can just make a table of values. So I did that for our previous example, for our non-abelian group of order 21. So this is sort of the character table of the characters of this finite group. And we always have a representation given by our Frobenius-Perron dimension that just spits out all of the dimensions of the simple or of our basis elements. And in this case, I have 4 other one-dimensional representations, which makes sense because this is a rank 5 ring. Now, you wouldn't notice this unless you'd somehow memorized all of the character tables for finite groups, but you'll see that this is actually the transpose of the character table of the group itself. So in general, the character table of our character ring for a finite group is always going to satisfy that. I just look at the columns of my character table of the finite group, and those are now the rows of my new character table. Okay. So in particular, you'll note that fusion rings don't have a trivial representation. They don't have a trivial character. There's no character that just spits out 1 for every basis element unless you're actually a finite group. So what replaces our notion of our trivial character is this Frobenius-Perron dimension. So this is as close to trivial as you can get, and it is always present for all of these fusion rings. So that's going to be quite important for these automorphisms. So if I have irreducible representations, you might have explored this before in your abstract algebra courses, and I have automorphisms, then you can compose automorphisms with irreducible representations to get new ones. Now, they might do nothing at all, and that very often happens. But sometimes when I take an automorphism and I compose it with an irreducible representation, I get a new irreducible representation. So this can be a good way to build out character tables, and it can be a good way to sort of differentiate groups, in fact. So we want to do the same thing for fusion rings. And when you do this for fusion rings which have fixed point free automorphisms, then you very quickly get this very important fact, which is in my paper. So if I consider fixed point free automorphisms of fusion rings of prime order, then those fixed point free automorphisms also act fixed point free on the irreducible representations. So again, this is treating our Frobenius-Perron dimension representation as sort of the trivial element. So that's always fixed, and all the other irreducible representations are permuted by that automorphism as well. So there's this sort of dichotomy between fixed point free automorphisms of fusion rings and fixed point free automorphisms of their characters. So the most important conclusion from this that we can draw is the following. So if I have a fusion ring with a fixed point free automorphism of prime order, then that implies that my Frobenius-Perron dimensions of all of my basis elements are integers. So this is not a common thing with fusion rings. If you compute the Frobenius-Perron dimensions of even the fusion rings of rank 2, you'll find that only one of them has integer dimensions. All the rest are quadratic algebraic integers. So having these fixed point free automorphisms immediately pushes us down into a much more controlled world. So these, what we would call integral fusion rings. So for a fixed, quick proof of this, basically, you know that our characters or irreducible representations are closed under Galois conjugacy. So if I take Galois conjugates of characters or representations, I get new ones. So if I did have a Frobenius-Perron dimension that lied in some larger algebraic number field, then that distinct Galois conjugate of my Frobenius-Perron dimension would also be fixed by my automorphism. And we can't have that by the previous theorem. So that means that every Galois automorphism fixes that Frobenius-Perron dimension. So it's a very straightforward thing to prove, but it immediately makes our study of these rings much, much simpler. So fusion rings are great. They're nice to study because of how combinatorial they are and how we can just compute everything on a computer. But we really want to get to fusion categories. And before I do that, I want to leave some sort of open questions just on the level of fusion rings. So you'll remember our very first slide was proving that a fixed point free involution of a finite group implied that the group was abelian, and then that was inversion. So I actually don't know if this is true for fusion rings in general. So the best I can do is prove that if the automorphism is what you would call centralizing, so the image of every element commutes with the element itself, then this implies that the automorphism is duality. But that's the best as I can do at this point. So the question is that the case in general? And moreover, does this imply that the fusion ring must be commutative? So this is a very interesting question. And whenever you try to apply the traditional proofs that were used in group theory, they don't tend to work for the fusion rings. So something new is going to be required here to prove this fact. So you'll also remember that the smallest non-commutative group that had a fixed point free automorphism was order or rank 64. So in terms of fusion rings, that's absolutely enormous. So the question is, first of all, is there an example of a non-commutative fusion ring with a fixed point free automorphism of prime order that's not just a group? And hopefully, if something exists, it's smaller than rank 64, but what is the smallest one if it does exist? That's a very interesting question to ask. And lastly, this sort of is inspired by a different result in group theory, which says that if I have a solvable group, then it has a one-dimensional representation that is not trivial. So in the future, when we talk about fusion rings, or fusion categories, excuse me, we'll see that it's possible that something like that would be true for these fusion category type examples. And as a result, these will have non-trivial invertible objects in them, those objects of dimension 1. So the question is this true on the level of fusion rings? I have not been able to find a counterexample, but is there an example of a fixed point free automorphism of a fusion ring for a ring that has no non-trivial invertible elements? Because it appears that there's always some group-like substructure in all of these fusion rings. So these questions are something that are approachable, I would say, even at an undergraduate level. Okay? They're very combinatorial and require very little prerequisite knowledge. So these are good things for someone to look into. But again, what I care most about is about categories that are built from these fusion rules. So I'll be very loose about this because the fusion category definitions can get very lengthy very quickly. So I'll just say that a fusion category is a semi-simple monoidal category whose Grothendieck ring is a fusion ring. So we want to take all of those axioms about fusion rings and just assume that rather than having equalities, we have some maps, we have some morphisms in our category that realize them. So rather than just having duals, we have these rigidity maps, etc. It gets very deep very quickly. But for the purposes of this talk, all we really need to know is that we have a semi-simple monoidal category whose Grothendieck ring is a fusion ring. And so really we're going to focus on having the fusion ring and saying that any fusion category that realizes it is called a categorification of that. Or we say that the ring is categorified by that category. So very often we don't really care what the structure of the category is specifically. We just care that it's realizing a certain fusion ring. So for examples that you're completely used to, if I look at the category of G-graded vector spaces, so finite dimensional, let's say complex G-graded vector spaces, then this is a categorification of the finite group ring itself. Or if I look at the category of finite dimensional representations of G, this is a categorification of the character ring of G, or the ring of irreducible representations, if you want to think about it that way. So these are things that we're already very familiar with, and they have very complex categorical structures that we already sort of slide under the rug because we're so used to thinking about them. Now, having a categorification is an incredibly rare property for a fusion ring to have. Many of my papers, and probably people who are going to be listening to this talk, have written papers just showing that rings don't have categories associated to them. They can't be categorified. So we're sort of looking at an intersection here of two very rare properties. Fusion rings which have categories that correspond to them, and having these very specific symmetries. So we're looking at a very small slice of the mathematical world, but that probably means that there's going to be a very nice description of these objects that we're trying to study. So just like we want to add more structure to our fusion rings in the form of categories, we want to upgrade our automorphisms to autoequivalences. So let's start out with a categorified fusion ring and an automorphism of that fusion ring. So we're going to say that there's a categorification of that automorphism if there's a tensor autoequivalence of my category, which restricts to that automorphism on the Grothendieck ring. It's exactly what you would expect. But again, this is an additional layer of structure. So in particular, there might be many different autoequivalences that restrict to the same symmetry. So for instance, there are fusion rings which have autoequivalences which are trivial on our objects, but they do strange things with the morphisms. So a similar thing could happen here. So just because we find one doesn't mean that there might not be lots of other ones floating around. So there are two main examples that I want to look at, and just in the interest of time, that's probably all I'm going to be able to talk about because I'm going to get distracted very quickly with some other topics. So the first example is the integral group ring for the cyclic group of order 3, and just the inversion swap of the two non-trivial elements. So we know that this has a categorification by C3 graded finite dimensional complex vector spaces. And in fact, and I'll not justify this entirely during this talk, this is categorified by a tensor autoequivalence, which switches those two simple objects of our category. So there is a categorification of this very simple example. But if we look at our favorite example from earlier, character ring of the non-abelian group of order 21, this also has a fixed point free automorphism that we already talked about, which is complex conjugation or duality, however you want to think about it. But this is not categorified by any tensor autoequivalence. So it is essentially the same operation. It's inversion or duality, but it's realized by a categorical structure in one case, and it's not realized by a categorical structure in the second place. And I will justify the second claim to some extent. But for now, just accept that, these are just examples of one being true and one not being true. So this brings us to my first distraction, which is fusion categories of odd dimension. Because if you look at these two examples, you'll notice that's exactly what these are. These are fusion categories whose Frobenius-Perron dimension, the sums of the squares of all of the Frobenius-Perron dimensions of the elements, is an odd integer. So one thing that's incredibly special about these fusion categories, which was proved by Richard Ng and Peter Schaumburg 16 years ago, was they proved that if your Frobenius-Perron dimension is an odd integer, then none of your objects are their own duals. So this is actually quite a surprising fact. There's no way that I would have thought that that would be true without seeing a proof of it or just checking a billion examples. So some people call these maximally non-self-dual, but really these are just the Frobenius-Perron dimension.
Non-trivial simple object, right?
Yes, sorry, non-trivial. So I'll remember to add that before I send these notes out. Yes. So again, like fixed point free, we're ignoring the fact that the unit exists. Okay. So thank you for pointing that out. Okay, so this is false for fusion rings in general. So this is very special about fusion categories. So we've already looked at the smallest fusion rings, rank 1, 2, and 3. And we've only found one non-trivial fusion ring that has odd dimension. It was just the group ring for the cyclic group of order 3. And that's obviously true. So if you look at the next more complicated rank, rank 4, you immediately find counterexamples. So here we have a fusion ring, which has dimension 15, Frobenius-Perron dimension 15. So that's an odd integer. And you'll notice that all of the basis elements, because of the symmetry of the fusion matrices, these are self-dual. Okay? So everything's self-dual, but we have an odd Frobenius-Perron dimension. So this is the very smallest example, but surely as you look at larger rings, that there's going to be lots and lots of things contradicting this. So the point is that fusion categories of odd dimension are sort of our best bet for creating a categorical structure which has a fixed point free tensor autoequivalence. Because now I don't have to worry about what the autoequivalence is. I don't have to prove that it exists. If I take any commutative fusion category of odd Frobenius per odd dimension, then that potentially has a fixed point free tensor autoequivalence of prime order, in particular prime order 2. Okay, so with that in mind, you start looking through your fusion categories of odd dimension. Excuse me, I knew I was going to sneeze there. You start looking through your fusion categories of odd dimension, trying to find an example that works. And it's actually quite difficult to find one that works. So you start looking at larger theories, which prove that they either exist or don't exist. So if you want to look outside of the obvious non-classical examples, which always work for instance, vec-G, for other reasons that I won't discuss, then your next place that you might look is at the doubles or the Drinfeld centers of these finite groups. So these are also going to have odd dimension, but they're going to have very interesting simple objects. So they're indexed by conjugacy classes of your group and irreducible representations of their centralizers. So they're huge. They're doubled or squared, or however you want to think about it, in size compared to the group. And you'd hope that these would have some interesting autoequivalences. But surprisingly, this produces 0 new examples. So examples that aren't already of the form vec-G. So specifically, if I have a finite group of odd order, then this duality map on the double is categorifiable if and only if the group is abelian, in which case the double is just vec-G for some larger group. So it's producing no new examples, no examples where my simple objects have large Frobenius per odd dimensions. So this actually is probably not a well-known fact. It's extracted from a paper called Unphysical Diagonal Modular Invariance, which is not where you would expect to find a result like this. But fortunately, I was already familiar with the paper by Alexei Davidov from about 8 years ago. So there you can find much more information, and you can find a description of some automorphisms of the doubles of finite groups. Unfortunately, they're not fixed point free in general. So this is all the information that I can get from this paper. So that's very disappointing. So far, we only know of trivial tensor autoequivalences, which are fixed point free, or come from classical finite group theory. So one way to show the opposite direction, which is to show that they don't exist in particular examples, is to look at a construction that comes from these autoequivalences. So if I have a finite group, say a group of prime order in our case, which is acting by tensor autoequivalences on my category, then I can create a larger category called its equivariantization. So if you're in the VOA field and you like the VOA language, this is sort of called the orbifold construction, or it's looking at the representations of the fixed point subalgebra when you have a group acting on your VOA. So something that's very common across all the languages in this field. So in our very specific context, I won't give a general description, but when we have our categorified fusion ring, and we have our categorified fixed point free automorphism of that ring, then our equivariantization is basically looking at the orbits of that fixed point free action, along with invertible elements that represent the group itself. So specifically, we're going to have an orbit for we're going to have a simple object for each orbit of our objects. And they're going to have dimension p times their original Frobenius-Perron dimensions. And then we're going to have the P simple objects of Frobenius-Perron dimension 1. Okay. So these correspond to the unit being a fixed point of this action. Okay. So we get a very predictable category produced from these autoequivalences. So remember, fusion categories are very difficult to exist in the first place. So if we have a more complex fusion category that we can construct from this, there is a chance we might be able to prove that this category itself does not even exist. So that'll be our goal with this equivariantization. One moment. Excuse me. So just for some examples of this, we'll go back to our very first example, which is with our inversion automorphism of vec C3, because I told you that that was categorified by a tensor autoequivalence. And that's just because these G-graded vector spaces are so simple, there's nothing preventing any automorphism of the group to lifting to an automorphism of the category itself. And what we get when we do this equivariantization, remember, we're going to get one simple object whose dimension is 2 times 1, which is 2. And that corresponds to the orbit of the non-trivial elements. And we get 2 one-dimensional objects, which correspond to the fact that the unit is a fixed point. So this category is just rep S3, or it's representations of C2 acting on that C3. So you can actually see the action in this fusion category. So we get something that we're very familiar with, and that's not quite our goal, but it shows this construction in action. So if we go to our example, which I claim did not exist, remember this was a rank 5 fusion category. And in fact, this ring is only categorified by one category. So you can find this in Eddinghoff, Galacki, and Ostrich's paper on fusion categories of dimension P times Q. So for the primes 3 and 7, this is the only fusion category that exists. So we know exactly what the fusion category is. And my claim was that its duality, fixed point free autoequivalence doesn't exist. Okay. So if we assume that it does exist, then we can do our equivariantization. We can collapse all of these orbits by the action. And we get a fusion ring that kind of looks familiar. In fact, this fusion ring is identical to the one that we used as a counterexample for fusion rings of odd order not being totally non-self-dual, except for one digit, this 5 down in the lower right-hand corner. So this is the only digit that's different from that fusion ring. So it's interesting that that one fusion ring, which really does not exist as a category, would appear very, very closely to this one through this equivariantization construction. Okay. So that's not quite a coincidence, because we can study fusion categories like this in much more generality. Oh, and just to note, the Frobenius-Perron dimensions are 1, 1, 2, and 6, as we predicted. So this is my second distraction, is this fusion ring right here. Because this fusion ring has a very large subring. It's the entire ring except for one element. So you could try to study these types of rings in general, and you find that they're very difficult to exist, even though they look like they would appear. So these are related to a lot of things that we're already very familiar with from previous research. So the most common one is what's called a near group fusion ring. So these are fusion rings which have a subring, which is an integral group ring, and it's size 1 less than the rank of our fusion ring. So you're almost a finite group, but you have one more possibly interesting element. And these have been studied for over 2 decades. And more recently, there's been a generalization of this, which has a horrible name. I did not pick it, generalized near group, which is where you have a subgroup of your ring that acts transitively on everything else in your basis. So in particular, the near group fusion rings are an example of this. So it is very literally a generalization. And I think the last paper I talked about in this seminar was on these types of objects. But I was recently introduced to a different generalization of near groups, which I call near integral. So we take the definition of a near group fusion ring, and we just remove the fact that our subring is a group. So you're allowed to have any type of subring imaginable, as long as its rank is 1 less than your larger ring. And I call these near integral because it turns out that the dimensions of the subring all have to be integers, the dimensions of the basis elements. So they're very close to integral, but they don't necessarily have to be integral. So there's a complete characterization of these on the level of fusion rings, which is quite interesting because the categorifications are very difficult. So this is ongoing work that I've been discussing with Jingcheng Dong. And the sort of main headline theorem from that work has been this classification. So a fusion ring is near integral if and only if there exists a column of its character table with exactly 2 non-zero entries. So it's very easy to detect these things if you compute character tables. You don't even need to know the fusion rules. So copious amounts of these examples arise from the character rings of finite groups. And this actually has been studied as far back as the 1980s. So remember, our character rings and their representations are sort of transposes of each other. So what Gagala was studying in the 80s was characters, so rows of the character table that have only 2 non-zero values. So now that we're looking at fusion rings, we're kind of looking at the transpose of that. And these are exactly the fusion rings with 1 column with that property. So this is very much the transpose of a group theory question. So these things appear a lot when you're looking at these equivariantizations of fixed point free automorphisms. So just for fun, I found an example. This is the automorphism group of D25. And it's this easy to figure out that there's a maximal fusion subcategory of this, because this very bottom row is all zeros except for 2 entries. So again, what this means for rep of this group is that it has a maximal subcategory, which consists of all of these representations which aren't dimension 20. So quite interesting. So let's get back to what we were trying to discuss in the first place, was the fact that I can't categorify this very nice symmetry of my fusion category. So again, we'll remember that this is the only fusion category with these fusion rules. So I can't twist it around to try to make this work. Auto equivalence, then I'm going to have a fusion category with these fusion rules. Now, I'm going to leave you with slightly a cliffhanger, or homework, I should say, which is the fact that this fusion category doesn't exist can be found in Jingcheng's paper on maximal fusion subcategories. So you'll have to look it up for the proof, but it just shows that studying these maximal fusion subcategory fusion categories has implications for these other areas of research as well. So this is another very interesting line of thought. So in the rest of my paper, what I tried to do is to find the smallest examples. So the smallest examples of fusion categories, which have potential tensor autoequivalences, which are fixed point free. So the only ones that even have the possibility of having this type of an autoequivalence, which are rank less than 8, which again is quite large when you're studying fusion categories. They're either integral group rings for groups of rank less than or equal to 8, or there are 3 character rings which just happen to be that small, and they're all of groups of order p times q. So they're all of the form that we've already seen. So someone's going to have to look at much larger fusion categories in rank to try to find more interesting examples, because there aren't a lot of very small ones. And this makes sense when you think about how far you had to look out to find a non-abelian group, for example, with a fixed point free automorphism of prime order. So it might be very, very large, our first interesting fusion category with one of these properties. So I want to end, I think we're approaching, about an hour here. I want to end with a conjecture that ties back to something that I mentioned before. So the conjecture is that if I have a categorification of a fusion ring, which one of these fixed point free automorphisms of prime order, then there's a notion of solvability for fusion categories. So I won't go into the definition now. It's not too important since this is just a conjecture, but it seems in all of my examples that all of my examples that I've found so far are related to finite groups in sort of an iterative way. So you can construct them all from finite groups in a very explicit manner. And that's essentially what solvable means for a fusion category, that it's not directly related to finite groups, but you can construct it using finite groups in some way. And that appears to be the case for fusion categories that have these symmetries. Now, the interesting part about this conjecture, if it was true, is that this would imply a version of the Feit-Thompson theorem for fusion categories. So the Feit-Thompson theorem, if you don't remember, says that every finite group of odd order is solvable. So the categorical version of that would be identical. So any fusion category of odd dimension is solvable. Or more generally, if you have one of these fixed point free automorphisms of prime order, then you must be solvable. Okay. So I don't expect this to prove Feit-Thompson theorem as a special case or anything like that. You most certainly would end up having to use it somewhere in your proof. You'd have to use Feit-Thompson for finite groups to prove this for categories. So although it's not going to be some groundbreaking result, it would be interesting if the exact same sort of result was true. And that's as much a testament to the person that proves it as it is to the people who came up with the word solvable. So that means that they picked the correct word for that definition. Okay. So that being said, good conjecture there and a lot of good questions about fusion rings before. So I hope you've seen enough examples to be convinced that this is something that really deserves a lot more study. Okay. So talking for about an hour, so I think I'll end it there. And thank you for listening.